In a number of video presentations on my YouTube channel, I have underscored thermodynamic non-ideality effects for binary mixture adsorption in microporous crystalline materials such as cation exchange zeolites and metal organic frameworks such as CALF20. Today, my focus is on adsorption of ternary mixtures in LTA-4A zeolite. And I want to ask the question, is it possible to predict mixture adsorption for ternary systems from data on the constituent binary pairs? I take as an example a mixture of carbon dioxide, propane, and methane adsorption in LTA-4A. LTA-4A consists of cages of approximately 11 angstrom in size. Each cage is separated from adjacent cages by windows of which are approximately 4.1 angstrom in size. The blue spheres are extra framework sodium cations, and these sodium cations partially obstruct the window regions, and diffusional limitations are particularly strong in LTA-4A zeolite. LTA stands for Lindner type A. The carbon dioxide gas molecules locate preferentially in and around the window regions. For example, you can see CO2 molecule nicely ensconced and straddling the window region. The alkanes such as propane and methane are primarily located within the cages. So there is segregation in the location of gas molecules within LTA-4A zeolite. I had earlier stressed the importance of segregation and congregation effects in CO2 capture with sodium X zeolite, also called 13X zeolite. Today, my focus is on thermodynamic non-idealities in LTA-4A zeolite. To illustrate and quantify segregation effects, let us consider a binary mixture of carbon dioxide and propane in LTA-4A zeolite. For a total pressure of 100 kilopascals with a partial fugacity of 10 kilopascal for CO2 and 90 kilopascal for propane, molecular simulations were used to determine intermolecular distances by sampling a total of 1 million equilibrated samples for mixture adsorption. On the basis of the sampling, we can determine the radial distribution function for various pairs of molecules. The red line is for CO2-CO2 pairs, and we see that the maximum occurs at a distance of 4 angstrom. and the CO2 sodium cation distances are approximately 3.8 angstrom, demonstrating that CO2 is located close to the extra framework cations that primarily are hovering around the window regions. If we look at distances of pairs of propane molecules indicated in green, we see that the average distance of separation is about 4.8 angstrom. The distances between CO2 and propane is indicated by the black line, and we see that the peak occurs at about 6.5 angstrom, indicating that the guest pairs CO2 and propane are further apart than the CO2-CO2 pair and the propane-propane pair. This implies that the competition between CO2 and propane is less strong than in the hypothetical case in which the guest molecules are homogeneously distributed within the pore landscape. Put another way, we have segregated adsorption of the binary mixture of CO2 and propane in LTA-4A zeolite. And this has consequences for the applicability of the ideal adsorbed solution theory. The ideal adsorbed solution theory of Myers and Prausnitz is based on a number of key tenets. All the adsorption sites within the microporous material are equally accessible to each of the guest molecules, implying a homogeneous distribution of guest adsorbates within the pore landscape. In other words, there is no segregation or congregation or preferential siting. In addition, there is no change in the specific surface area of each molecule on mixture adsorption, and the molecular clustering due to, say, hydrogen bonding is not catered for by the IAST. I refer you also to other video presentations on the real adsorbed solution theory and the spreading pressure concept that is available for viewing on my YouTube channel. Here are some of my papers that provide the theoretical background. Since the IAST requires a homogeneous distribution of guest adsorbates within the pore landscape, we should expect non-ideality effects to be prevalent for CO2 propane mixture adsorption and LTA-4A zeolite. Let's see if that is true. To quantify thermodynamic non-ideality effects for CO2 propane mixture adsorption in LTA-4A zeolite, 3 different molecular simulation campaigns were undertaken. In the first campaign, the total fugacity of the mixture was maintained at 1 megapascals and a temperature of 300 Kelvin, and the mole fraction of CO2 in the bulk fluid phase mixture was varied from 0 to unity. And the molecular simulation data for the adsorption selectivity of CO2 with respect to propane is plotted as a function of mole fraction of CO2 in the bulk gas phase mixture. We note that there is a selectivity reversal that is experienced for mixture adsorption, and the composition at which the selectivity of CO2 with respect to propane is unity is the azeotropic composition, and has a value of approximately 0.1. The ideal adsorbed solution theory anticipates no dependence of the adsorption selectivity on the mixture composition, and this IAST prediction is indicated by the dashed lines, whereas the molecular simulations indicate the occurrence of selectivity reversals, a sure sign of strong thermodynamic non-idealities. Two further molecular simulation campaigns were carried out for 1090 mixtures of CO2 and propane. The total fugacity was increased from very low values, say 1 Pascal, to about 10 to the 7 Pascals, and the CO2 propane adsorption selectivity determined from the CBMC simulations. CBMC stands for Configurational-Bias Monte Carlo simulation, is plotted as a function of the surface potential. The surface potential is a proxy for the spreading pressure pi, and the spreading surface potential is pi times the specific surface area per kilogram of framework divided by R, the gas constant, times the absolute temperature T. The surface potential is calculated from this expression, where P sub 1 superscript 0 and P sub 2 superscript 0 are the sorption pressures, and the integrals are evaluated such that the surface potential or the spreading pressure for mixture adsorption equals the spreading pressure for component 1 and equals the spreading pressure for component 2. If the mixture were to behave ideally, the adsorption selectivity of CO2 with respect to propane would show a unique dependence on the surface potential that is a proxy for the spreading pressure. And this IAST prediction is indicated by the dashed line. In reality, we have strong deviations from the estimates of the IAST. Indeed, for 1090 mixtures, we have selectivity reversals at this surface potential value of, say, 28 moles per kilogram. This is the CBMC simulation for an 80-20 mixture of CO2 propane. In this case, no selectivity reversal is observed for the range of surface potentials that are considered. So there are strong deviations from the behavior anticipated by the IAST. And to quantify the deviations from the IAST, we have to introduce activity coefficients in the expression that relates the partial fugacities to the sorption pressures P sub I superscript 0, and Xi is the mole fraction of component I in the adsorbed phase mixture. The activity coefficients need to be quantified and modeled in order to be able to quantify the variation of the adsorption selectivity with either mixture composition and or the surface potential phi. For the three sets of CBMC simulations shown in the previous slide, I plot here the activity coefficients for CO2 and propane as a function of either the mole fraction of CO2 in the adsorbed phase mixture or the surface potential. For the campaign in which the total bulk fugacity is maintained at 1 megapascal, we see the activity coefficients have the limiting behavior that as the mole fraction of the adsorbed component I approaches unity, the activity coefficient of that component should also approach unity. For the other two CBMC campaigns, for a 10-90 mixture and 80-20 mixture, we have another requirement for the activity coefficients, and that is that as the surface potential approaches 0, the activity coefficient of both gas molecules should approach unity. This is because the surface potential also serves as a proxy for the pore occupancy. So as the pore occupancy approaches 0, then the gas molecules are far apart and there are no thermodynamic non-ideality effects. So we should have the limiting behavior that as phi tends to 0, the activity coefficient of that component of each component in the mixture should tend to unity. So if we say adopt a Wilson model for quantification of the activities of components 1 and 2, then we should introduce a correction factor 1 minus exponential minus a constant c times phi, and this is a representation of the pore occupancy. And as this quantity approaches 0, ln gamma 1 will approach 0. In other words, gamma 1 should approach unity. Similarly, ln gamma 2 should be proportional to 1 minus exponential minus a constant c times the surface potential phi. So as phi tends to 0, ln gamma 2 tends to 0, and gamma 2 tends to unity. The three constants lambda 12, lambda 21, and C can be determined from the three sets of CBMC simulations by applying a regression analysis. And with the choice of these parameters, the molecular simulation data for the three campaigns may be reproduced in a quantitatively correct manner as shown in these figures. For binary mixtures of carbon dioxide and methane, two different CBMC campaigns were undertaken. The blue triangles represent the CBMC data for the adsorption selectivity for CO2 methane mixtures in the proportion 1090. The inverted pink triangles are the CBMC simulations for CO2 methane adsorption selectivity for 50-50 mixtures. The two sets of data show different selectivities, and the dashed lines are the IAST calculations for the CO2 methane adsorption selectivity. The IAST anticipates that the adsorption selectivity for binary mixtures is uniquely dependent on the surface potential. And the CBMC simulations show that this is not the case for CO2 methane adsorption, because the 50-50 mixture, the adsorption selectivity is significantly lower than the adsorption selectivity for 1090 mixtures. And to quantify deviations of the CBMC data from the IAST estimates, we introduce activity coefficients, and the activity coefficients for CO2 indicated by the red circles, and the methane gas molecules indicated by the green squares are shown here. The continuous red solid lines are the predictions of the real adsorption solution theory using the Wilson model with fitted parameters indicated here. Mixtures of methane and propane also indicate deviations from ideality, and in this graph we show molecular simulation data for 10 mixtures of methane and propane, and we see that the adsorption selectivity of methane with respect to propane is significantly higher than the predictions of the IAST. Here are the activity coefficients for methane and propane as a function of the surface potential. The continuous solid black lines are the RAST Wilson models with the fitted parameters indicated here. So the three binary mixtures, CO2 propane, CO2 methane, and methane propane, all three binary mixtures show deviations from thermodynamic ideality. Now the question is, can we predict the behavior of ternary mixtures of CO2, propane, and methane on the basis of the information of the unary isotherm fits for the three constituent guests and the Wilson parameters that have been fitted for the three separate binary pairs. In order to test the predictability of the RAST Wilson model, we conducted ternary mixture adsorption simulations using configurational-bias Monte Carlo simulations. The ternary mixture simulated using CBMC was a 25-65-10 mixture of CO2, methane, and propane. The component loading for CO2 indicated by the red circles, green squares for methane, blue triangles for propane. The CBMC data on the component loadings are compared with the IAST estimates indicated by the dashed lines, and the continuous solid lines are the RAST estimates using the Wilson parameters as fitted for the three constituent binary pairs. This is the multi-component extension of the Wilson model using the Wilson parameters for the three constituent binary pairs as shown in the foregoing slides. The predictions for the component loadings are in reasonably good accuracy with the simulated data using CBMC. The activity coefficients for the three guest molecules are plotted here and compared with the RAST Wilson estimates using the ternary version of the Wilson model that includes the correction for the surface potential phi. The message that emerges from this slide is that ternary mixture adsorption equilibrium can be predicted with reasonably good accuracy from information on the thermodynamic non-idealities for the three constituent binary pairs.